what is the sum k equals 0 up to n of 5 to the k? Okay, so how do we do this? Right, so we know, remember, like the most basic generating function that we know of is this thing 1 over 1 minus x is the sum k equals 0 to infinity of x to the k. And another very basic generating function that we have is this one. If I take the same generating function, so I take the same thing 1 over 1 minus x, and I just multiply this by x to the n plus 1, right? Then what this does is basically it adds an n plus 1 to the exponents. So the first kind of equality here, I'm just rewriting 1 over 1 minus x and then times x to the n plus 1. I can pull that x to the n plus 1 inside the sum, right? So I haven't done anything that interesting there. But now I can change the kind of limits of the summation. So if I think about it here, I take the term k equals 0, right? It has, if when k is 0, I get x to the n plus 1. When k is 1, I get x to the n plus 2, etc. I can think of this as just starting my k at n plus 1 and taking x to the k. So formally, if you wanted to do this slower, you could take do some sort of substitution or something. But hopefully it's clear why why this equality holds. So then if I want to just compute, like I take this sum and I just want the first n elements, that's like taking all the entire sum to infinity and subtracting the terms where the exponent is bigger than n. And this is the sum, which is the terms that are bigger, where the exponent is bigger than n. So I can rewrite this as 1 over 1 minus x. So this thing in the yellow minus the thing in the green, x to the n plus 1 over 1 minus x. Okay, and so if I wanted to compute this with x equals 5, I can just plug it in, right? So I get, here I get 1 over 1 minus 5 minus 5 to the n plus 1 over 1 minus 5, which is, okay, so there's a lot of negatives going on here, but if I multiply by negative 1 on the top and bottom, I get 5 to the n plus 1 minus 1 over 4. So that's the final answer. So most people, I mean, if the majority, the most common answer was this one. There was a few which were similar, just maybe off by 1 or something. So in the exponent, yeah. So some people are now answering it after I've answered it, which is, yeah, that's fine. One thing to notice is that one thing that's kind of weird here is that, so I want to just briefly highlight, is that here's the thing, you can't, if I take this thing, this infinite sum, if I tried to plug in 5, it would just give me infinity, which would be, so I can't really, you kind of can't plug in 5 here, x equals 5 here. And likewise, you also can't plug it in here because that'll also give me infinity. But somehow, like, even though it's not valid to put in 5 into either of these things, if I take this thing, which is, and I can still express it this way, using these things I can't plug in 5 into, but this is still a valid equality. And then I can, now I've got this thing which doesn't diverge. So this, I can plug in 5 here because it's a finite sum. And so what I'm trying to highlight here is that this equality is still valid, even though I wasn't able to plug in 5 here, I wasn't able to plug in 5 here, but at the end I can. So that's just a comment there. Okay, so are there any questions about that before we move on? The chat is somehow getting frozen, not coming up. It sometimes does that. I'll maybe come back to it once the chat pops up. If it ever does. Here we go. What exactly is the sum in green? Yeah, exactly. It's the terms that are past n. Yeah. So, and you can work that out by just kind of knowing that this is x to the n plus 1 times the yellow thing, and then kind of putting the x to the n plus 1 inside. And then you see that the only terms that are getting counted are x to the n plus 1, like when I put k equals 0, or when I put k equals 1, it's x to the n plus 2, plus 3, plus 4, etc. So then I could just rewrite this by saying, I'm just going to kind of change my index. The index is k. Instead of starting at k equals 0, I could just say, I'm going to start at k equals n plus 1, but I'm going to write x to the k, and that's like the same sum because it starts at n plus 1, goes to n plus 2, etc. So yeah, it is counting the things past n. And if we take all the things and we subtract the ones that go past n, we get the ones from 1 to n, or from 0 to n. Okay. So we're kind of moving on to, okay, so this is a topic which is very related to the generating function stuff, but it's a little bit of a different topic. So it's going to be recurrence relations. We're partially following chapter 9 in Keller and Trotter's book. That's the kind of main course textbook. But there's a few parts of this chapter which I'm not that happy with how they do it, just because it seems unnecessarily complicated in a sense. So for those parts, we will be partially following section 2.4 in a book where the author's name is Levin. So it's called like an open introduction, Discrete Mathematics, an open introduction or something. So in the course schedule, so we've always had these links to the textbook in the course schedule. So there's links to this in the course schedule. Okay, so yeah, we're going to be talking about recurrence relations for pretty much the rest of the course. I guess actually the whole rest of the course. So a recurrence relation is it's just an equation. So you have a sequence. Okay. So imagine I have a sequence A0, A1, A2 up to infinity. A recurrence relation is an equation which expresses, let's say, the nth element of the sequence as a function of some of the elements that came before it. So formally speaking, imagine we have a sequence A1, A2, A3, A0, A1, A2, A3, A4, etc. It's a sequence of numbers, and f is a function. And if I have an equation that looks like this, where an is equal to f applied to an minus 1, an minus 2, down to an minus k, this is something that we call a recurrence relation. So what this is saying is that a recurrence relation is basically instructions for saying what is an given the choices of an minus 1, an minus 2, down to an minus k. So it defines an in terms of the previous values. We're not really going to need to. So if you're having a hard time internalizing this kind of abstract definition, it's not really going to be a problem because most of the types of recurrence relations we're going to look at have a kind of simple form. So really it's important to understand the simple types of recurrence relations. So here's an example. This is a very famous example, the Fibonacci sequence, or the Fibonacci numbers. So the way you get the Fibonacci sequence is from the following recurrence relation. So my sequence is going to be f0, f1, f2, f3, etc. I define f0 to be 0. I define f1 to be 1. And then for all the rest of the values, so if I have fn, I define it to be fn minus 1 plus fn minus 2 for n at least 2. So just to be clear, like on the definitions, like this part of the information here, this is what we call the initial conditions of the recurrence or of the sequence or whatever. So initial conditions is just like defining a few kind of individual values. So f0 is 0, f1 is 1, and this part of it, the definition, is what we call the recurrence relation. So this is an equation which gives you instructions for how to make the nth term of the sequence from the n minus 1 and the n minus 2 terms. So what is the Fibonacci sequence? So it starts with 0 because f of 0 is 0. It goes to 1 because f1 is 1. And then this one is going to be the sum of the two previous ones, right? So it's 0 plus 1 is 1. This one is 1 plus 1 is 2. So for this one, I add up the 2 and the 1, I get 3. And then 2 plus 3 is 5. 3 plus 5 is 8, and so on and so forth. Is this example clear? And are these definitions okay? Recurrence relation and stuff like that. So this was right. So this Fibonacci sequence, it was introduced by some person called Fibonacci way back a a long time ago. And their interest was studying the growth of rabbit populations. So the idea was like, imagine you have an island with 0 pairs of rabbits. I introduce 1 pair of rabbits at time 1. And then every month, let's say those rabbits reproduce. And when they reproduce, let's say they produce a pair of rabbits. And this kind of looks at how many pairs of rabbits are there at time n. Okay. And that's assuming that none of the rabbits ever die, which is possibly a weird assumption. Okay, here's another example of a recurrence relation. So one thing we want to get good at is, so sometimes you might be given a combinatorial problem, like a word problem, and part of your task is to take that word problem and transform it into a recurrence relation, and then maybe to solve the recurrence relation. So let's see how we can transform a problem into a recurrence relation. So let an be the number of binary strings of length n which don't have any consecutive ones. So there's no 1 that's followed by another 1. Okay, so let's look at some initial conditions. So these are going to be my initial conditions. So a1 is just 1, or sorry, 2. I should try not to mess it up right from the beginning. Because a length 1 string, there's 2 of them. And obviously a string of length 1 doesn't have consecutive ones. So what is a2? Can anyone help me out with that? My computer really seems to be having difficulties today with Zoom, but so the chat will probably come up at some point. I assume people are getting the answer 3, because, all of the strings of length 2 are good, except for that one. So I've got 3 good ones of length 2. Okay, so now what is an? So here's the thing. So here's how. So I want to come up with a recurrence here. Now, if you think about it, so if I take so I want to kind of say that if I take a string of length n minus 1, and I want to make it into a string of length n, there's kind of 2 choices for the nth letter, the nth symbol. So it's either a 0 or a 1. If I have a string of length n minus 1, okay, I can always add a 0 at the end. When can I add a 1? So I can add a 1 if the string ends in a 0. If my string of length n minus 1 ends in a 0. How many valid strings of length n minus 1 end in a 0? Well, it's equal to the number of valid strings of length n minus 2. Because if I take any good string of length n minus 2, I can always add a 0 to the end of it. So this is actually my recurrence relation. So sorry, I was kind of messing it up before, but is that clear? So I've always got one choice for how many ways I can put the nth letter. It can always be a 0, but I get an extra choice if my last character was a 0, because I can also put a 1 after it. So that gives me this relation. Right. So this is an example of how to transform a question about strings into a recurrence relation. Okay, and really later what we're going to need to do is learn how to actually solve these recurrence relations to get the general formula. So a very similar example, if I take ternary strings which don't have a 2 followed by a 0, maybe for now I'm going to skip this example because it's very similar to what we did before, but this is also worth thinking about. So I believe this one might be in the textbook as well. Here's a more interesting example, which is kind of quite different from the strings. So suppose I take n lines in the plane such that you don't have 3 lines intersecting in the same point. So the thing that's forbidden is I don't have anything like this, right? So my question is, how many regions do these n lines split the plane into? So I put down n infinite lines in the plane. I don't have any 3 that intersect in the same place, so they all these intersections are kind of separate, and I want to know how many regions are there. And so here's an example. So I borrowed this example from the book. So what is R1? So R1 is the number of regions you get or Rn is the number of regions you get with n lines. So if I draw just one line, then that one line splits the plane into two parts, right? So R1 is going to be 2. What's R2? Okay, if I draw two lines, it's going to give me 4 regions, 1, 2, 3, and 4. Right, so R2 is 4. Now how can so here's the kind of general case. So I want to get now a recurrence. So maybe this, what I mean here is maybe for R at least 2 or something, n at least 2. So suppose the number of regions, so I know how many regions n-1 lines make. And now I'm adding an nth line, and I want to say how many regions do I have. So imagine we've added 2 lines. And now I'm going to add a third line. Okay. So right now we have 4 regions. 1, 2, 3, 4. Suppose I'm going to add a line like this. Okay. Going through here. Right. So as I add this line, I start in one of these regions. And when I cross one of the lines, I can think of that as splitting the region I started with into 2 different regions. So we get one new region here, right? So this is the one we had before. Used to have all of this, and we kind of get a new one here. And now I follow along, and when I reach the next line, I now get a new region here. And then I go off to infinity, and this cuts another new region. And here's the cool thing about lines. If I have lines in the plane, 2 lines can only cross once, right? So maybe I should also say that these are not parallel. Because if they're parallel, then everything could be quite different because they don't cross. So, okay, so if you think about it, so every time I touch one of the old lines, so I'm making my nth line, every time I cross one of the old lines, I add a new region. And then when I go off to infinity, I add another new region. So actually, Rn is going to be Rn minus 1 plus n. And you can kind of, in this picture, you can kind of check the calculation. So like what we're saying is that R3, when I add my third line, that's the same as R2 plus 3. And 3 is accurate. Like 3 is the number of new regions we made by adding that line. Okay. So actually, this is kind of nice because it doesn't actually even matter about the geometry of how you put your lines down. No matter how you put down the lines, the number of regions n lines will be the same as the number after n-1 plus n. So it satisfies this recurrence relation. Okay, so you need to be able to come up with recurrence relations from word problems like we've done here. You're also going to need to learn how to solve recurrence relations. So how to get a formula for the nth term of a recurrence. And so that's what we're going to learn next. But first of all, are there any questions at this point? So, okay, so we're going to focus mainly on some very special types of recurrence relations. Until maybe in one of the last 2 lectures of the course, maybe I'll talk about a nonlinear recurrence. But all the ones we're going to focus on, mainly are linear recurrence relations. So the way they work is that an, right, so a linear recurrence relation is that an is defined as a kind of linear function of the previous k terms for some k. So it's like a constant c1 times an minus 1, c2 times an minus 2, ... down to ck an minus k. And then maybe plus some other function, like let's say plus n or plus 2 to the n or some function of n. So this function of n, it doesn't depend on the sequence a, but it's just some like plus n or something, for example. And we say that it's a linear recurrence of order k if kind of the number of steps it looks backwards is k. So it's a linear recurrence of order k if it looks like this, so c1 an minus 1, an minus 2 ... times ck an minus k, where ck is not 0, which means that an depends on the k previous steps. So that's what, if I ever say order, so we're really, to be honest, in this course, we're only going to look at relations of order 1 or order 2. So an order 1 relation is like an equals constant c an minus 1 plus some f of n maybe. So that's order 1. And order 2 is like an is, say, can minus 1 plus b an minus 2 plus maybe f of n. So the order is how many previous steps you look back. And we say that the equation or the recurrence relation is homogeneous if this f function that depends on n is 0. So where an just depends completely in terms of the other things. So for example, like this one we just looked at, so we had Rn is Rn minus 1 plus n. So this is a non-homogeneous recurrence relation because it depends, like the nth step depends on n. Whereas this other example we looked at is homogeneous because it's like an is just an minus 1 plus an minus 2. Any questions about that? So let's see how much you can already do without me teaching you how to solve these recurrences. So what is the solution to the recurrence relation a0 is 5 and an is equal to an minus 1 plus 2 for n at least 1? So what is, so suppose I assume, a0 is 5, an is an minus 1 plus 2. What is an? Okay, we're getting a few answers coming in. Any more answers? So I suggest kind of thinking about what happens, right? I start with 5. What is a1? It's 5 plus 2. What is a2? It's 5 plus 2 plus 2, right? So I think, so if we kind of start writing these out, a0 is 5. a1 is 5 plus 2, which is 7, right? a2 is a1 plus 2, so it's 7 plus 2, which is 9. a3 is 9 plus 2, because it's the previous 1 plus 2, which is 11, right? So we can kind of see what pattern is emerging, right? So an is just 5 plus 2n, right? So when I say that I want you to solve a recurrence relation, that's what I mean. So I want you to tell me what is the function, what is the kind of formula for an. So this was a kind of simple example. So you can already do this even before I've taught you. Here's another one. So suppose I take this recurrence relation. So again, a0 is 5, but this time an is 3 times an minus 1. So what's an? Okay, so we got 5, right? a1 is 5 times 3. Oh, sorry. The previous one times 3. a2 is the previous thing times 3, right? 5 times 3 times 3, which is 5 times 3 squared, right? And I guess we can see the pattern that an is 5 times 3 to the n. So these are, the easiest type of recurrence relations you're going to see. And we're going to try to build up methods for doing more complicated things. So one example, I think at some point we might look at this example, like what if I mix these two things, right? So before we had an is an minus 1 plus 2. Here we had an is an minus 1 times 3. What if we took so you can see that these things, if you think about this example, you'll see that things get a little bit complicated pretty fast. What if I take an is 3an minus 1 plus 2? So I just combine these two examples. And it's doable. We're going to be able to do it, but it's not so obvious what the answer is going to be. Okay, and we're going to be able to do much more complicated things than this as we go. We're going to build up the tools. Okay, so the kind of the trick I want to teach you today, or the kind of method, is going to involve setting up a telescoping sum. Okay, do you know what a telescope is? Right, it's like, oh dear, I can't really draw this. Right, a telescope, right? It's a thing for looking at space, right? And maybe sometimes you can push the thing together, right? So that's the kind of thing we're going to do. We're going to have some kind of sequence of numbers, and they kind of get pushed together. But you'll see how, and things cancel. Basically, a telescoping sum is try to make everything cancel. But let's see how that works in this example. So okay, so remember this region in the plane recurrence? So we had R1 is 2, right? One line splits the region into two, or the plane into two regions. Rn is Rn minus 1 plus n for n at least 2. So I want to kind of get a formula for Rn by doing some kind of trick where I make a bunch of things cancel. So I think this is a really slick trick. And we're going to get a lot of use out of this. So here's one trivial observation. So this is my recurrence relation. That's fine. For reasons that we're going to see in a second, it's going to be more useful for me to write this. So I'm just going to pull the Rn minus 1 to the other side. So Rn minus 1 is equal to n. Nothing fancy so far. So suppose I just write this out, okay? And below it, I'm going to write out the same recurrence relation, like the same equation, except for n minus 1 instead of n, okay? So my first one is like this on the top. And below it, I write down the recurrence relation for the previous step. So if I take r sub n minus 1 minus r n minus 2, I get n minus 1. So that's just kind of, you can think of plugging in an n minus 1 where the n's are. Okay. So all of these equations should be true. So if I take Rn minus k for some k, and I subtract Rn minus k minus 1, oops, there's a typo here, that should be equal to n minus k. And that goes all the way down to the first kind of step of the recurrence, which is that R2 minus R1 is equal to 2. Okay. And now here's the cool thing. Think about what happens if I sum up all of these equations. So I sum up all the left sides of the equations, and I sum up all the right sides. So can anyone see what's going to happen on the left side? And this is the telescoping cancellation thing. It's like, what happens to like my Rn minus 1 here that's being subtracted here? Well, it's being subtracted here, and it's being added on the next line. So if I sum up the left-hand side of this whole thing, so these are going to cancel, right? And I've got a negative Rn minus 2 here. And on the next line, which is not, so I haven't written the next line, but it's Rn minus 2 minus Rn minus 3. And so there's a positive Rn minus 2 on the next line, which is going to cancel. So this one, by the way, won't cancel. And if you think about it, this one won't cancel because there's no line below it. But everything else is going to cancel. And that's like the beauty of this kind of telescoping thing, right? So if I add up all of these things, I get that all of these things cancel, except for my Rn at the beginning and my minus R1 at the end. And then if I sum up the right-hand side, I just have n plus n minus 1, n minus 2, dot, 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 down to 2. So that gives me a very simple equation. It's just Rn minus R1 equals this sum. So yeah, so this is, so kind of writing this out formally, like what I've done here is like, I kind of summed up, so we kind of write all of these equations that rk minus 1 equals k, right? And I sum this for all k from 2 up to n, right? And we can see that everything comes up with a positive and a negative, so those cancel, except for Rn minus R and R1, and then I get still the same thing on the other side. So is that clear? I think this is a slick trick. This is and so actually this gives us completely just gives us a formula for Rn, right? If I just pull the R1 to the other side. So are there any questions about what happened here? Because you're going to have to know how to reproduce this in other examples. Okay, so, but by the way, what does this give us as a final answer? It gives us that Rn, so R1 was 2, right? That was our initial condition. So if I plug that in and I move the R1 to the other side, and what is the sum? So suppose I take the sum, so what is this sum? Or, okay, a kind of easier, more familiar one is if I take 1 plus 2 plus 3 up to n. What's that? So we've done this at some point, maybe in multiple ways. So what if I add up the numbers 1 up to n? What do I get? Yes, right. n times n plus 1 over 2. And so this sum that I have here on the right side is the same as that, except minus 1, because the 1 is missing. And now I'm going to add 2 to that, because from the R1, so I move that to the other side. So my final answer is that Rn is n plus 1 over 2 plus 1. So this is an example of how you can solve these recurrence relations. using this kind of telescoping trick. So just to be clear, what do I mean by telescoping? So yeah, so this is a general thing in mathematics, that a telescoping series is a sum of the form, I equals 1 to n of ti, such that there exists a sequence a0, a1 up to an, such that ti is equal to ai minus 1. Okay, so that's what a telescoping sequence is, or a telescoping series, or telescoping sum, maybe. And the kind of cool thing about these telescoping sums is that if you write it out, so if I sum up ti from I equals 0 to n, so the 0, maybe from 1 to n. Yeah, 1 to n. That's what I started with here. The first term is a1 minus a0. The second term is a2 minus a1, because just by the kind of definition here. Then I'm going to have a3 minus a2, and so on. And everything shows up with a positive and a negative, except for an and a0. So when you sum up a telescoping series or sum, then it just equals an minus a0, where, for whatever sequence is like the telescoping thing. So it's kind of like, yeah, you have this long series here. And the reason it's called a telescoping series is like, you can imagine you have your telescope and you kind of push it together and it ends up at this very short thing. So I'm not sure if that description helps, but yeah. Okay, so this is just what we, this is what we computed on the before. So this is our Rn. It just equals n times n plus 1 over 2 plus 1. One thing I should maybe mention is that there's so sometimes you're asked to find a general solution to a recurrence relation, and sometimes you're told to get a particular solution subject to the initial conditions. So suppose I didn't know that R1 is 2, right? I can still, just by knowing the recurrence, I can still get a formula for Rn. I can say that Rn is equal to R1 plus this thing, right? So that's what we would have gotten here, right? If I take this equation, I solve for Rn, it's R1 plus that sum, which is n times n plus 1 over 2 minus 1. And so this would be, I would say that this is the general solution to the recurrence relation Rn equals Rn minus 1 plus n. And then when you plug in R1 is 2 into this, then we say that this is like a particular solution to this recurrence relation with subject to the initial condition that R1 is 2. So hopefully, I think in all the problems you'll encounter, it'll be clear from context. Like if I give you some initial conditions and I say to solve it, then I want the particular solution for those initial conditions. But if I just say find the general solution, then you can leave it in this form. Now here's one great thing about this part of the course. Like in other parts of the course, like enumeration, for example, you would try to count solutions to things or whatever, and you get an answer, but it's hard to check your answer unless you want to try a whole bunch of cases or something. In this case, for recurrence relations, it's pretty easy to check your answer because all you have to do is check that it actually satisfies the recurrence. So you just plug things in, right? So I got this kind of final answer here. If I want to check it, I just have to check the initial condition and I have to check the recurrence relation and see that they both hold. So to check the initial condition, I just look at R1, which means I just plug in n equals 1. You plug in n equals 1, you'll see it's equal to 1 times 2 over 2 plus 1, which is 2. And remember we said R1 is 2, so this checks the boxes. This is correct. And then you have to check whether the recurrence relation holds. So the way I want to do that, it's kind of often more convenient to write it in this way where I've subtracted Rn minus 1 to the other side. So if I plug in Rn minus 1, I just plug in my function here. It gives me, it's technically this plus 1 minus this thing plus 1, but the 1's cancel. And in the end, if you do the algebra, you get n, which is what you wanted to get. So therefore, the answer we came up with is correct. because it satisfies the recurrence relation and the initial conditions. Now, of course, if this is a test and you have time pressure, then maybe you don't have a chance to check every answer. But for example, on an assignment, you can always check if it satisfies the recurrence and the initial conditions. And if it does, then it's right. Okay. Are there any questions at this point? So remember, we had these two examples before where we had an is an minus 1 plus 2, or an is 3 times an minus 1. So let's try to combine these two examples together. So a0 is going to be 5, an is going to be 3 times an minus 1 plus 2. And I want to get a formula for an. Okay, so I want to solve this recurrence relation. So for all of these things, there's more than one way. I mean, there's more than one way to skin a cat, they say. There's more than one way to do this. But for these ones, the way that I think simplest is to deal with kind of this telescoping sum idea. So try to set up a telescoping sum, and we will learn other sorts of methods as well. But let's look at this one. So let's try to repeat the steps we took last time. So what did we do last time? We started with our recurrence relation. We subtracted to put the a minus 1 thing, n minus 1 thing on the same side as the an thing, right? So we have an minus 3 times an minus 1 equals 2. And then what we did was we wrote down the same thing over and over, except for, so we did it for an minus 1, an minus 2, an minus 3, down to a1. And our idea was to just sum up all these equations and hope that everything will cancel. Last time it worked beautifully because remember I had like a rn minus 1, and then I had an rn minus 1 minus rn minus 2. And these things just magically canceled out. But it looks like I've got a bit of an issue here because these don't cancel. Because I've got a minus 3 here, but I've only got a plus 1 here, right? So if I add these up, it won't cancel. But if you think about it, this isn't the end of the world. Nobody told me I have to add up just the equations as they are. I can manipulate the equations before I add them. And one thing that seems useful here is, what if I take this second equation and I multiply it all by 3, right? So then I've got 3an minus 1 minus 9 an minus 2 is 6. That's still valid, right? That's still true, because if I take a true equality and I multiply it by 3 on both sides, remember it has to be on both sides, don't forget, that it's still true. And now if I look at my first line and my second line, now things are looking good. These are going to cancel when I add it up. So what should I do to the third line? So any thoughts about that? So my equation before was an minus 2 minus 3 an minus 3 equals 2. What should I do to it to make this telescoping trick work? And again, Zoom is kind of slow, so I don't know if anyone's answered or not. But okay, so, well, I should multiply it by 9 because I see a 9 here. So I take this one, I multiply it by 9. And what I see is that, so this becomes a 9, that becomes a 27, and the 2 becomes a 18, right? And there's a pattern here. So basically, if I take the kth level of this of these equations, and I multiply it by 3 to the k, then if you think about it, everything is going to cancel up nicely. So here's what I do formally. So I take, so the first level, I just leave it as an minus 3an minus 1 equals 2. The second level, I take my equation, I multiply it by 3 on both sides. Remember, it has to be on both sides. The next one, I multiply by 3 squared, which is 9. And so on and so forth. The kth level, I multiply by 3 to the k. And we go all the way down to the level a2 minus a1. And actually, we want to go even one more level, 3 to the n minus 1, a1 minus 3, a0 is 3 to the n minus 1 times 2. And if you kind of look what happens, then all of these things are going to cancel except for the first an and the last like a0. Because, for example, if I look at an minus 2, I've got 3 a minus 3 here, it gets multiplied by 3, and then I've got a 3 squared here, right? So these cancel, that cancels, everything cancels, except for this thing and that thing. Is that clear? So for whatever reason, I decided, I think in my notes, at some point, I have switched from A0 is 5 to A1 is 5. So let's maybe pretend it was like that from the beginning, because otherwise I have to keep changing all the notes. But okay, let's suppose A1 is 5. It doesn't really make a difference conceptually to what we're doing, but let's just assume that. So so A0 is not defined, it just starts at A1. Okay, so what do I get here? So when I sum it up, so like I said, I've still got AN, it doesn't cancel. I get a minus 3, so this is the one that doesn't cancel, so I've got a 3 here, and I've got a 3 to the n minus 2 here, so I get 3 to the n minus 1, A1, and then that equals 2 times this sum k equals 0 up to n minus 2 of 3 to the k. So that's the same sum here, except I've just defined, instead of k's, I'm doing it in terms of I, but it's the same. Now, this is where the poll question becomes relevant. Remember, in the poll, I asked you to compute the sum of 5 to the k equals 0 up to n, right? This is a very similar type of sum. It's just that we're summing 3 to the I, and it goes up to n minus 2, but otherwise it's basically the same thing. So by all this generating function stuff we've done, we know that if I want to compute the 1 plus x all the way up to 1 plus x squared, x cubed, up to x to the n minus 2, it's the same as taking this, so which is this thing minus that thing. And again, by writing out the generating functions, you can see how this works, because all the powers which are n minus 1 or bigger will cancel. I plug in x equals 3, so I plug in x equals 3 here and here. I get 1 over minus 2 minus 3 to the n minus 1 over minus 2, which, if you cancel some minus 1s and stuff, gives you this. And this finishes everything, right? AN is this. A1 is like 5 or whatever. So I can just plug in a 5 here. Then I've got 2 times this summation, and I've worked out the summation. So that's the answer. So AN is 5 times 3 to the n minus 1. So here I've got this. This works out the summation, but I have to multiply it by 2, because in my formula it's 2 times the sum. So that cancels the 2's, right? And so I get A1 times 3 to the n minus 1 plus 3 to the n minus 1 minus 1, which is, if you do a little bit more algebra, it's 6 times 3 to the n minus 1 minus 1. And like I said, you can always check these things. So if you plug in n equals 1, you can check that it equals 5. And if you take an minus 3 an minus 1, you can check that it's always equal to 2. So our answer is correct. Any questions about that? So hopefully from these two examples, you're getting a feel for how you can do these telescoping sums. So this poll is related to, so sorry. I changed it to, at some point as I was solving, so I got messed up, I guess, when I was writing the slides, and I changed it to A1 at some point. So sorry about that confusion, but Okay, so here's a question. So I've given you 1, 2, 3, 4, 5 sequences. So an equals 2 to the n, or 2 to the n plus 1 minus 1, blah, blah, blah. Which of them is the solution to this recurrence relation with this initial condition that a1 is 3? And if you're ever given some options like this, I would suggest not to go through and solve the recurrence relation, because that takes some effort. So the hint is that you don't actually have to solve the recurrence. So any thoughts about what's not the answer, for example? So I think, for example, if I take 2 to the n, right, that's not the answer. Because, for example, if I just take a1, it's supposed to be 3, but here it would be 2, right? If I take 2 to the 1, it's 2. What about 2 to the n plus 1 minus 1? Does that have a chance? If I plug in 1, I get 4 minus 1. So this is a maybe. So I'm just checking the initial condition. If I take 2 to the n plus 1, plug in n equals 1, that gives me 2 plus 1 is 3. So that's a maybe. That could work. 2 to the n minus 1 or plus 1, that cannot be the case because if I put in 1, I get a 2. So that one's not. So I've basically got two options now. So these ones are ruled out. I've got these two options. And now you just say which one satisfies the recurrence. So let's look at this one. So if I take, for me, the easiest way is always to write the recurrence like this. So I've just pulled over the an minus 1 to the other side. And we say, is this true if I plug in, so I'm going to do this one, 2 to the n plus 1. So is it true if I plug in that this holds? So if I take 2 to the n plus 1 minus 2 times 2 to the n minus 1 plus 1, right? So what does that equal? So it's 1, so it's, okay, 2 to the n plus 1 minus 2 to the n minus 2, which is a minus 1, but that's not 1. So that kills this one. So this one is not a maybe anymore, it's a no. So it must be the last one. And if you went through and checked the recurrence, I think, unless I've messed it up, hopefully this is correct, that this does satisfy the recurrence, and so it is the answer. So if you ever have options that you can try, then you can always just check which one satisfies it. Okay, let's do another example. So suppose a0 is 3, and an is 5 times an minus 1 plus 2 to the n. So let's try to solve this using the same trick. So my first step, as usual, I write down the recurrence for an minus 1, an minus 2, all the way down until I reach the smallest one that works, which is a1 minus 5a0, right? And I can't go further than this. It doesn't make sense to go further, right? And now I look at this and I say, does it already telescope? And the answer is obviously no, because I've got 5 of these and I've only got 1 of those. So they're not going to cancel. But so I just multiply by 5s, a whole bunch of 5s. So here I've got 5 times my second equation, 5 squared, 5 to the k. So the kth line gets multiplied by 5 to the k. And remember to do it on both sides. And now again, when you think about it, so if you think about adding up both sides of these equations, you are going to get cancellation now because I've got 5 of these here, and I've got 5 times 1, so 5 of these on the next line, and these ones are negative and those ones are positive, so these will cancel. I've got 25 here, 5 times 5, 5 squared, because I've got this 5 times this 5, and I've got 5 squared here, so these will cancel, and that's going to cancel all the way down except for this one and that one. Okay, so the left-hand side, so I'm doing this one a little bit faster than the last one, but hopefully you're kind of seeing the pattern. So the left side is going to be an minus 5 to the n a0, because if you look at it, my coefficient of a0 is going to be 5 times 5 to the n minus 1, so it's 5 to the n. And the right-hand side is this complicated looking thing because, so I haven't really been talking about the right-hand side very much, but so in the nth step, it's 2 to the n. The n minus 1 step, it was 2 to the n minus 1, like before we multiplied by 5s, and then 2 to the n minus 2, etc., right? Just using my initial recurrence, right? And then I'm multiplying every line by more and more 5s. So I've got kind of like, on the top line, I have like 2 to the n, 5 to the 0, and then I've got 2 to the n minus 1, 5 to the 1. And so every line is like, 2 to the n minus k, 5 to the k, which is weird. Like I've got one exponent going up and the other one going down. But we can handle this. This is not too bad. Just takes a little observation that, okay, and this is an obvious thing, but 2 to the minus k is the same as 1 over 2 to the k. And here I've got I don't have 2 to the minus k, I have 2 to the n minus k, but you can always pull the 2 to the n out in front. So I pull out the 2 to the n. I've got now, when I pull out the 2 to the n, I've got 2 to the minus k, 5 to the k. The 2 to the minus k becomes a 1/2 to the k. I I kind of put it together. I've got 5/2 to the k. And we've got the same, now we've got the same kind of thing as before. We're using this equation, which you can get from generating functions. And I just plug in x equals 5/2. Okay. And so this gives us a solution to the right-hand side of the equation. And now we just solve for an. So all I'm doing here is now taking this 5 to the n a0, moving it to the other side, and that gives you your final answer, which turns out to be 3 times 5 to the n, because I think a0 was 3, 2 to the n, blah, blah, blah. I mean, this is just all algebra, and that's the answer. So which a very strange kind of answer. Okay, so that's all the examples I have for you today. Next time, we'll start with a little bit more complicated example of this type. So again, using this telescoping trick, and then we will move on to second order recurrence relations. So second order recurrence relations are things like the Fibonacci sequence. So for example, we'll do second order things, which, for example, Fibonacci, fn equals fn minus 1 plus fn at minus 2. Okay, so are there any questions? Or if not, we can just end it here. Yep. Yeah. Okay, yeah. So what was that? Oh, yeah. Let me. So should I find the slides? Should I open the slides for that one? Okay. Sorry, the computer is struggling. Maybe if I. Okay. So I'll open. Okay. So this was lecture 15. Let's go to the derivative one. So which part was it? So this is this one. Okay.